All right, so now that you've finished your lab, we need to talk about what we were able to learn. So once it was discovered that charges exert forces on each other, we wanted to know quantitatively how did that force depend on a couple things like the charges and the distance between them. And so that's what you did with your lab. You first of all asked how does the force between two charges depend on the magnitude of one of the forces, Q2 for example, and what you found was that the force was proportional to the charge. When the charge got twice as big, the force got twice as big. There's a direct relationship. The second thing you found was that as the distance between the charges got bigger, the force got smaller. And you probably were able to eventually figure out that if you graph 1 over d squared, there was a direct relationship between the force and 1 over d squared. So we say this is an inverse square law. So the force is proportional to 1 over the distance squared. As the distance got bigger, the force got smaller. So I think that's what you found in your lab simulation. So in 1785, Coulomb published his theory of charges, and we now call this Coulomb's result, or Coulomb's law. And it looks like this. So you might take a minute to jot this down. It's in your toolbox. But it basically says that the force between two charges is equal to the product of the charges, so Q1 times Q2, divided by the distance squared, times some constant, which we call Coulomb's constant. And this never changes. It's always the same. And it's the absolute value of that result. So sometimes Q1 might be positive or negative, Q2 might be positive or negative, but it doesn't matter. This equation always tells us the size of the force, just how big it is, not what direction it's going. So that's why there's absolute values here, the magnitude. So this Coulomb's constant is 8.99 times 10 to the ninth. And this is in Newton meters squared per Coulomb squared. So that just tells you that the forces have got to be in newtons, distances have got to be in meters, and charges have got to be in coulombs. It is possible to find this constant in other units of measure, for example, using feet instead of meters, but then it's a different constant, and of course you'd have to solve all the problems using feet. But this constant, write it down, it's an important one, and the units on the constant tell you what units you need to use to solve the problem. All right? So let's solve an example problem with that. Actually, before we do, back up a little bit. Coulomb's law is also called the electrostatic force, and it's basically the force that governs all of chemistry. The reason that sodium and chlorine stick together and form a solid, salt, is because of electrostatic force, the force of attraction between the sodium ion, which is short an electron, and the chlorine ion, which steals an extra electron and produces a net negative charge. And those two positive and negative charges are attracted to each other and cause them to join together, and you get an ionic bond. There's also covalent bonds, but these are all just electrostatic forces. And so really Coulomb's law can explain basically all of chemistry, although it gets really, really complicated figuring out what's going on with all those forces between all those different things. This electrostatic force is an inverse square law, just like gravity. So a quick check. If I have two balloons and the distance between those charges gets 3 times bigger, what will happen to the force between them? Well, if the distance gets 3 times bigger, the force has to get 9 times smaller. So that's an inverse square law. Okay, so what we now know is that positive charges are located in the proton. So the proton has a positive charge. There's more complication to it than that, but we're just going to try to keep things a little more simple here. There's actually things called quarks, and there's up quarks and down quarks and all kinds of different quarks. And some quarks carry 2/3 of a charge, and some quarks carry negative 1/3 of a charge. And a proton is made up of a certain combination of quarks. But anyway, all of that to say, a positive charge is in the nucleus, it's carried by the proton, and the electron carries the negative charge. And the electron is this particle-like thing which kind of acts sometimes more like a cloud than a particle, and it zooms around. Robert Millikan at the University of Chicago was able to deduce the charge on one single electron, and he found it was negative 1.6 times 10 to the minus 19 coulombs. See, when we first found charges, we had no idea what they were from. And so we decided to use a unit of charge called a coulomb, which turns out to be an enormous number of electrons. And a single electron has a charge of negative 1.6 times 10 to the minus 19 coulombs. So we're going to use this as a conversion factor. One electron And negative 1.6 times 10 to the minus 19 coulombs, that's the same thing. That's the same charge. So we can use that as a conversion. Okay, and then of course the proton isn't really a different number. It's the exact same number. It's just a positive charge instead of a negative charge. And if you have an electron and a proton together, the net charge is 0. You add these two together, you get 0. So an electron and a proton together are neutral. Okay, so let's do a quick little example here. Suppose I have a small little conducting sphere and it has 1 billion extra electrons on it. So however many protons there are 1 billion more electrons. And I want to know, what is the charge Q on this sphere? So 1 billion is just 10 to the ninth. So I have 1 times 10 to the ninth electrons. And what I'm going to do is I'm going to use this as a conversion factor. I want to get rid of electrons and I want to end up with coulombs. So I put 1 electron on the bottom and the 1.6 times 10 to the minus 19 coulombs in the top, so that the electrons cancel the electrons and I'm left with coulombs. So take 1 times 10 to the ninth, multiply it by negative 1.6 times 10 to the minus 19, and you get negative 1.6 times 10 to the negative 10 coulombs. So that's still 10 to the negative 10 coulombs. It's still a really, really tiny amount of charge as measured in coulombs, but that's 1 billion electrons. Okay, so if you had a charge in coulombs and you wanted to know how many electrons it is, you would use this conversion factor also, except you'd put the coulombs on the bottom and you'd put the electrons on the top to cancel the coulombs. We're going to use metric prefixes a lot, so a quick reminder in case you're not sure, you can pause this and jot them down if you don't already happen to have them. But centi is 10 to the negative 2, micro is 10 to the negative 6, and those are the ones we're going to use a lot. All right, so let's solve an example problem, which is very similar to the one you're going to do in your homework set. So if I have 2 balloons, they're 15 centimeters apart, and that's the distance between their centers. And I want to know, what is the force on them if each balloon has a charge of about 1.2 microcoulombs. So a microcoulomb is a typical charge you can generate by rubbing a balloon on your head for a couple minutes. And so that's what we're going to use. All right, so here's my diagram. The distance d is always between the centers. I've got Q1 and Q2. I'm going to write down what I know. So the force is unknown. The distance is 15 centimeters, and I just need to substitute in what centi means. It means times 10 to the negative 2. So 15 times 10 to the negative 2 is 0.15 meters. The charges are the same. Q1 equals Q2, and those both equal 1.2 microcoulombs. So instead of micro, put in 10 to the negative 6. They mean the same thing. So there's my variable list. And now I just need to evaluate Coulombs' law. The magnitude of the force will be K, Q1, Q2 over d squared. K is a constant, it never changes, so just put it in, 8.99 times 10 to the ninth. Make sure that you've got coulombs for your charge, so those coulombs are going to cancel with those coulombs. That meters squared is going to cancel with those meters squared. Run that through your calculator, and go ahead and give it a try, just make sure you can get it. You should get 0.58 newtons. And it's important to remember that these absolute value signs tell us that this is a signless number. It's just 0.58 newtons. That's the force. That's the size of the force. If you want to know what direction that force is going, you're going to have to look at the geometry of the problem. So for example, if you are looking at the balloon on the right, if these are both positive charges, those two balloons repel each other. So the force on Q2 is going to be to the right. So if I said, what is the force on Q2? You could say, well, it's positive 0.58. But if I said, what is the force on Q1? That's also being repelled. And so the force on Q1 is to the left. So that would be negative 0.58 newtons. So the equation here just tells us how big the force is. You're going to figure out the direction of the force based on the geometry of the problem, which object it's acting on and whether the charges are the same or opposite charges. Okay? All right, so we're going to practice using this equation right here. Now, physics is a really boring spectator sport. You're probably bored already, and this has only been about 8 minutes long. So, in order to have a little more fun, you've got some problems to do. So this would be a great time to stop and work on problem set H 9.1. This will give you some practice in the kind of problems we've been doing. When you get near the bottom, you're going to get some more complicated problems, which involve arrangements of charge, like 3 charges, and when you get there, there will be a link to a video to kind of show you how to work through those. But it will make most sense if at this point you stop and go ahead and solve the first bunch of problems in homework 9.1, practicing Coulombs' law, which is this equation right here. and solving for Q1 or Q2 or D or F. Okay? All right, good luck.